Hello, everyone. It's our last session, but not the least. I first know Charles on a blog post on the N-Micro, which is an open source advisory company, I believe, or consulting company, I believe. Anyway, they say now you can have a completely open source RISC-V SoC to boot Linux, and you can synthesize it, place and route it, and finally generate a BGen to the kind of FPGA with completely open source portion. I was like, wow, this much. I think that will be a slow process. I guess. Back then, I was thinking, this is open source. I think the performance won't be good, and I was wrong. Dead wrong. Totally wrong. VexRiscv could play a Doom on it and can play the MP3 and all kind of multimedia on it perfectly with just a CPU resource without any DSP or any kind of multimedia processor. And after 1 year of the first time I get to know this project, the VexRiscv and the SpinalHDL, which is awarded to be the champion on the 2018 softcore design the contest is the first prize. So it has SMP now. You can have a completely RBD32 GC RISC-V core, and it can do all the kinds of stuff. It's just amazing. And without further ado, we will let Dolu to do the presentation.
Hello, welcome to this talk. So I will introduce you how you can use software to describe and generate some digital hardware. So you can do that by using VXLAN and Verilog, which are hardware description language. That's what most people do. Or you can use other ways. There is, for instance, HLS or Dataflow and many other solutions. But one of the solutions you can use is named, in a general way, Internal Domain Specific Language, or EDSL. And the concept of that is you can use a general purpose programming language with a given library, which will provide you an API to describe what you want. For instance, if you want to generate some XML file, maybe you can find some internal domain specific languages to make this easy for you. Or maybe, but in our case, we will use that concept to generate hardware. And this is some Scala code, which uses a SpinalHDL API to define this hardware here. So let's read the example. So we want two registers which are connected to each other. So here it is a low-level API of SpinalHDL. It's not normally what we use, but for the example, that's what I will use. So you can define, okay, I want a bool thing in my hardware design. I will set its name to reg1. I will specify that this thing should behave as a register and not as a control signal. Then you can define the second thing as name as reg2 as well as a register. And then you can say, for instance, okay, I want my second thing to be assigned from the first thing. So I want reg2 to be assigned from reg1. And what we are doing here is we are programmatically describing the design that we want in a very explicit way. We really say what we want. We are not inferring things like in Verilog and VXDL. We are really being explicit about what we want. And so this is, as I said, the low-level API. It is quite verbal. So here is an example of a smooth API that you can also use. Basically, one concept in internal domain-specific language is to use a lot of makeup to make things smooth. So you can say, okay, I want reg1 and reg2 as register of the Boolean type. Then I want to assign register 2 to register 1, and so on and so on. And basically, also another concept of internal domain-specific language is that each time you use the API of that library, so in the given case, SpinalHDL, it will be registered into the database. All of your actions are registered into a database. For instance, when you create a bool, it will add this in the database. And the database will keep a trace of it. So it will remember everything you wanted, like this bool, and this assignment. And then what it will do is translate the database into a synthesizable VHDL or Verilog file. That way, you can generate your design and use it into the regular flow to deploy it on FPGA or ASIC. So if you want to go on FPGA, you can use Yosys or NextPiano. If you really have to, you can use vendor tools like Vivado and Quartus and also others. And yeah, that's the concept. So basically, it can look a bit a lot of overhead. Yeah, it can look like some overhead to have to use a general purpose programming language like Scala with API like SpinalHDL in order to generate hardware instead of directly using VxDL or Verilog, which were kind of made for that, but not really. So, but the thing is, that's the main selling point of SpinalHDL. It is embedded into a general purpose programming language because what it allows you to do is to use all the strong aspect of a general purpose programming language to manipulate your netlist, to manipulate your design, and you can use it as an elaboration tool. So when I mean elaboration, it means the equivalent of VxDL and Verilog for loops, which are not something that you put into the hardware, but it helps you to elaborate what you want. And basically, you can use all the software aspects of Scala as an elaboration tool for your hardware. So let's look at the example. It's a dummy example, but try to keep things not too complicated. So let's define an array of things which are registers. So, okay, I can use, for instance, the Scala collections, like a mutable array buffer, which is really a Scala thing of the type bool. Then I can, for instance, add those registers into that mutable array, like using a for loop and simple things. So, and then, for instance, if I want to create a new array, which will be the inverted values, you can say, okay, I want to take my first array, things, and map a new array from it by using this transformation function. I want to revert the value. So it is not a SpinalHDL thing, it's really a Scala thing that is functional programming used to transform collections. And you can use that as an elaboration tool to fill the netlist with what we want. Another example of that is when we want to check if all of those values are true. So we can take our array logics and use the concept of reducing it to a single element by using this reduction function. Like if you want to, this function say like, if you have two elements, you can reduce them to one using the AND gate. And it just works. You can do this kind of thing. So here I used functional way, you can use for loop way, you can use many other things. In other case, you can use hash map, dictionary, hash set, all this kind of data structure applied to hardware elaboration. So yeah, like I said, all the features of software we can use, like classes, type parameter, lambda function, I/O, like reading and writing files, can seem stupid, but in VxDL and Verilog, that's not something you can always do because the tools will not necessarily support it. Functional programming, abstract interface, itinerance, and abstraction layer is also a strong point of it. There is many places in the hardware where it makes sense to use that. Often it's when you have kind of repetitive structure like a pipeline or streams. You can use data structure to model those, and is the hardware description which has those elements. So once you can define hardware, you also need to do simulations because in hardware, it's once the hardware is deployed it's really hard to debug it. It's really hard to probe things which are in a FPGA. And even if tools make it easy, it takes a lot of time to do. So really important to do simulations. And of course, you can use VxGen and Verilog to run simulations, but you can also use software to do that. One very popular example of this is CocoTB. And there is kind of an equivalent in SpinalHDL where basically, let's look at the example. Let's imagine they have a design with two inputs, A and B, that are multiplied together. Then we use a register to sample them each clock cycle. When there is a reset, we want our register to be cleared. And this is put on a given output. So here is the SpinalHDL description of this. So here it is written in a very compact way. It's not necessary, but for the example, like here, the result is an output register, which will sample each cycle, the given expression, and which will have a reset value 0. Okay, so here we have the hardware. Now we want to run a simulation of that. So we create a simulation configuration on which we will capture the wave of our simulation into a FST file, which is what you can see here. So a wave in hardware design is a chronogram on which the vertical axis you have your signal, on the horizontal axis you have the time. And then you want to compile on that configuration our top level, our design. And then once it's compiled, you want to run a simulation on it, and you will get a dude. So the dude is designed under test, and it is what represents our simulated hardware. And on that dude, you can access input and output from the software world. Like you can read the signal result, you can write the inputs from the software world. And basically what we do here, we say, okay, on our dude, take the default clock domain, please generate the reset and the clock signal behavior on them with a period of 10 units of time between each cycle. And then what we will do on this test bench is generate a sine wave which accelerate and a cos wave which accelerate. So to do that, we need some variable to store which phase of the sine and the cos we are, at which rate the phase will accelerate, will move. And basically, here we are in the main simulation thread. You can, in that API, create new simulation threads to have concurrent behavior. You can also define that on that clock domain, you want this code to be called each time there is sampling, like a raising gauge on it. And what we will do here, for instance, is use the Scala mathematical functions, sine and cos, to generate our A and B inputs. We will assign them with this operator. We will manipulate our phase. And so here, so we specify we want this function to be called each raising gauge. And then we will wait 2000 cycles before finishing the simulation. So we are really defining some concurrent behavior here. And this will give us this wave. So, and again, here is the wave, a Solomon wave. The idea here is because VxGen and Verilog were not designed as programming languages, they have a lot of weaknesses. And because here we are in a proper general purpose programming languages, we can use all the features again. Exactly as I said before, all the features, you can use them to write your test bench, to write reusable elements of your test bench. Can be really powerful. And so now that we have the ability of writing digital design and simulation software, we can also go further. Why not trying to define a CPU with all of this? So you could define a CPU in a very regular way, which is to define, to write, it's a bit a caricature, but writing each stage of your pipeline in different components. But let's try to model things. Let's try to model the structure of our CPU in software and then generate the hardware corresponding to it. So CPU here will be like a simple CPU, 5-stage, with front end to read the instructions and decode, execute, memory, write back. That's a stage structure, and that structure you will have some different elements to add behavior like the integer ALU, branch, load and store, decode, register file. So when you think about it, if you try to structure it, you can think like, okay, let's say I want to create a new CPU, which will internally define that there is those stages, decode, execute, memory, write back. And we will provide to this CPU as a parameter a list of plugins which will implement those behavior. Like you will have int ALU plugin to define the ALU. You will have decoder simple plugin to decode the instructions. So here we're not giving a parameter like should the ALU be 64-bit or 32-bit. We are providing as a parameter of the CPU directly the behavior. And we will see that in the next slide. So if we want to see how this is modeled, so here is an example. Like my CPU will be a component which take a Scala list of plugin. A plugin being a class with a setup function. So for instance, the setup function will be used by the integer plugin to ask the decoder plugin to decode the add instruction. Or for instance, it will be the setup function will be used by the branch plugin to ask the fetch plugin to provide him an interface that it can use to order branching somewhere. So the setup function will be used by plugins to ask each other things. And once all plugins ask things to each other, then we can have a build function to translate, to allow the plugins generating the hardware required to implement all their behavior and the behavior asked by other plugins. So this is what is a plugin. And if you go back to the CPU, so in the CPU here is defined that we have 4 stages like decode, execute, memory, write back, which are stages. And what is a stage? It is a structure which is composed of, it's mostly the arbitration. We'll see later some things added in it, but it's mostly the arbitration. Like, is an instruction valid in the given stage? Is the given stage stuck by some side effect? Should the current stage be discarded because some instruction downstream cancelled thing? And then in the CPU, at elaboration time, we can call the setup function of all our plugins and then call the build function of all our plugins. And things will build themselves that way. And this is how VexRiscv was designed. So this is a simplified demonstration of it to make things more readable, but that's really based on that concept. And so here are some examples. Like, as I said before, like you have a plugin which manages the program counter and other plugin which want to branch. So for instance, the branch plugin will ask the PC plugin to create a jump interface that will be used in the execute stage. So we have to specify in which stage we want to jump because there is some priority, like this interface has more priority than this one, which has more priority than this one. And then, for instance, the branch plugin will use that jump interface saying, okay, now I want to jump 2x. And basically the PC plugin implement a abstract software interface, which is a tray in Scala, jump service, which asks the PC plugin to implement that create jump interface function. So it's really mixing software and hardware. Like the software is used to model the structure of the hardware we want, and then we flush it into hardware. Then another example, really fast. So for instance, the concept of program counter is something which go through the pipeline. And for instance, here it is from the front end and used in the write-back stage when an exception occurs. And it is great if everything is really fixed. You always know how many stages you want and where you want to pick things. But the day you want to add a new stage, it is a mess because you have to repipeline everything. I mean, not really smooth. So here the idea is let's define the concept of program counter as a stageable value of that data type. So here we're not defining a signal, we're defining the concept of program counter shared through the pipeline. And then, for instance, in the PC Manager plugin, we will insert the program counter in the decode stage with the value X. And in another plugin, the one which manages the exception, we'll say, okay, I want to read the input program counter of the write-back stage. So the plugins only need to specify where they want things, and the framework will automatically pipeline things. So, and here's an instance of a full SoC, which was deployed on .devkit with two CPU, two VexRiscv CPU, capable to run Linux, 108 MHz. It's not really fast compared to modern standard, but for FPGA it's not bad. And keep in mind, those FPGA are really not the fastest available. Apart from that, so it implement each of those CPU implement integer operation, multiply, divide, atomic, floating point, double precision floating point, and compress instruction set. The FPU is shared between the two CPU to save area. There is a DDR3 controller, there is a SD card, Ethernet, USB host, video output, audio output. All of this design is SpinalHDL with Scala. Here is an overview of the structure of this SoC. It mostly focuses on the interconnect, like having a few CPUs with a shared FPU. JTAG to debug the SoC with required logic to manage atomic, required logic to handle memory coherency between the CPU and the DMA, the peripherals, the DDR3, calibration pass, I mean all those things. And one aspect of the SoC is that those components need to negotiate things between each other in order to have things working. You may not need to do that for simple SoC, but as soon you start to have features like memory coherency, eventually atomic, you start to need some some negotiation between components, especially for the interconnect. And basically, one way to do that is to know everything in advance, but that's often quite difficult. So what was done in that SoC framework, which is SaxonSoc, is that it uses software concept. Maybe you already hear of that, like it's await, async, future. The idea is to have some kind of concurrent hardware elaboration. So here is an example. Let's define A and B as integer handles. So a handle in that framework is something which will later on store a value. Not yet, later on. And here is another way to create a handle. So here it creates empty handles. Here you create a new handle, which will be named calculator. And this handle, when you create it, it will execute this code asynchronously to the main thread. And it will first try to get A, but A yet is empty, so it will block here until A is loaded with a value. And then they also create a new handle, another handle, which will print the value of calculator, but it will be blocked too. Once it will try to execute this line here, this gate here, calculator is not fully, is not loaded yet, so it will block that. And finally, at the end of all of this, we will load A and B handles with values, which will unlock this handle to, it will allow him to calculate A and B, A plus B, which will be loaded into the handle calculator, which will then unlock this handle, which will finally print the result of A plus B. So it's a really stupid example, but that's really the concept. Basically, you can define things in advance, you can define behavior in advance before you have all the requirements to execute them. And the SoC was elaborated using that concept. So really fast, the boot sequence. So first the FPGA need to load the bit stream from the SPI flash. Then the first stage bootloader will calibrate the DDR3 timings, copy a few binaries from the SPI flash, like OpenSBI and U-boot. Then OpenSBI is like a BIOS. It will manage all the low-level things like timer, serial communication, inter-CPU interrupts, equals from Linux. Then we have U-boot, which will fetch the Linux image from a SD card or from a TFTP server or from a USB flash drive. And then it will make Linux boot, which will initialize all the peripherals, and most important, will mount the file system, which contain build load. And finally, we are in user space, and we can run many applications. Like that's an instance with mainly X11, where there is a MP3 file which is streamed on a USB helmet. We have a web browser, we have Hashtop, we have image viewer, very important SL. I mean, yeah, and it runs really at a decent fluent level. It can also run Doom between 35 and 40 FPS. It can also it can run OpenTTD recently. I mean, yeah, there you go. You have a full system which can run Linux and apps on it. So that's it for my talk. There is a few links if you are interested. Like obviously all those projects are open source. Everything is up there on GitHub or other things. Nothing is hidden. So yeah, thanks for your interest. Have a nice day.
Hi, Dodo, can you hear me?
Yeah.
Okay.
Hi.
Hi.
You hear me?
Yeah, I can hear you. So I will pull the Q&As on. Can you see the screen sharing that I'm opening a Q&As?
Yeah.
Okay, the first one. What are the drawbacks of Shiso which urged you to invent SpinalHDL? Well, if memory serves it correctly, I believe there was a wiki page created by you to some kind of criticize Shiso's design, I believe, but it's gone. I can't find it anymore.
Yeah, I think you're right. So basically, because I was not, I mean, it's a lot of history. Basically, it started with Chisel 2. I started doing Scala and hardware design with Chisel 2 for some projects. I mean, to answer the full question, and then I will go to that. And basically, at that time, Chisel was not really in a good state, not at all. So basically, I started SpinalHDL as an experiment to understand how you can do internal domain-specific languages, and I ended up continuing it until the point it is now. As a bad state, I mean, like multiple clock domain was broken. A lot of of checks that I would like it to do were not done, like linting kind of checks. I mean, there is a lot of reason, and a lot of it could be reason like Chisel is more Verilog oriented, Verilog inspired, while SpinalHDL is more VXDL inspired. That can resume a bit the thing. Not completely, but the thing is that now today they moved on Chisel 3. And because I'm not keeping great track of Chisel 3 and not to cast bad shadow on the project, I just pushed away the page, which was listing all the issues which were on Chisel 2 at the time I experienced it.
Okay, thanks a lot for the insight. So basically, Chisel 3 is just fixing every issues you think is bad design, and so you remove the page, right? I get, because no, I was opening the GitHub issue page and looking at your comment. Finally, I know what happened. Sorry.
It's not because they would have fixed the issues. It's because I didn't keep track of the state of Chisel. But I guess quite a few things are still there. Quite a few, mainly, especially the Verilog versus VXDL safety and kind of things like this. This aspect still remain, I guess. For instance, you can assign a 10-bit into a 8-bit in Chisel. You can't do that in SpinalHDL. You have to acknowledge that assignment. Clock crossing also, I think it's not checked in Chisel. It is checked in SpinalHDL. I mean, there is many aspects. I mean, not go into details, but I would say there is many quality of life things which differ between the two languages.
I see. And the next question is, which build tool you prefer personally, Neo, SBT, or Gradle? Oh, this is regarding the Scala, I believe.
Yeah, that's the Scala build script. That's a bit like the makefile we use for C, but for Scala. Basically, I'm using SBT because that's the default. To be honest, I don't really like SBT. But it does the job. It does the job, and that's only what really matters for me for a build script. I'm not really in love with it, but yeah, I'm not really investing time with Mill and Gradle. I would say I would avoid Gradle as much as possible, but I have no real experience with it, really. So I can't give a proper answer to that question.
I see. Never mind. I think it's still haven't met someone who like. Oh, by the way, speaking of SBT, sorry, let me use the privilege as host to extend the topic a little bit. SBT is, I believe, it's very notorious to have the dependent of the version of Java. I tried to run SBT on the latest Java. I believe it's Java 12 or Java 11, I believe, and it breaks. I don't know why, and I need to downgrade my Java back to Java 7 or Java 6, I believe, and it's just absurd to have a build tool to have such strict dependency on the version of its host language. This is just
right. Also, for instance, often some people ask me if I can upgrade the SBT version, but unless there is really an issue, I never move this, because I know you change the SBT version, things break on some platform and not others. It's not great.
I can totally relate to your pain, because it is just anyway. Okay, next question. Any commercial use of SpinalHDL are you aware of? What's your plan to widen the language adoption? Are you providing consulting service professionally? Oh, I'm +1. Can I pay you to teach me how to write SpinalHDL?
So I know that there is, I will not say many, because I can't say, I don't know how much, but there is really companies using it. Often I'm surprised, like they suddenly come with me when they are given advancement of the project to ask about something. So that's a bit an issue with open source, because I don't have clients. I'm not really, I'm not selling license of SpinalHDL, so it's really hard to keep track of who is using the language. But for sure, many people and companies. Some people working in security, some in fast trading. I don't exactly know. That's the main thing about it.
I see.
About
So-
widening the language adoption. So basically, because it's not really a business, I don't really have a plan to extend the thing. Basically, my goal, I would say, in life, because I mean, I'm doing that mostly for fun, and now I have enough freedom to really work on that full time. It's just to have a great tool to avoid VXLAN and Verilog. That's the main point of me. And basically, I'm just trying, when there is issues, when there is feature requests, I try to be responsive, and that's my plan, to widen the language adoption, just make it good, and hopefully it will come naturally. And are you providing consulting services professionally? Yes, I am. Mostly, I'm trying to avoid implementing projects because it's a time sink, and it doesn't scale. So what I'm trying to do is, if a company asks me, eventually some little features in SpinalHDL, I can add for them if they need to. But mostly it is providing training to a company, like moving on site or doing remote training. I'm doing some of that.
Okay, fully understand. And this one's actually coming from me. How well is the VGA output simulation doing within the SpinalHDL? I believe at some point I traverse around the SpinalHDL code, and I see that it seems to be some kind of firm buffer emulation in the SpinalHDL framework. How well is it supporting, or how well is it doing?
So it is okay. This is right. Yeah, there is in SpinalSim. So in the simulation API in SpinalHDL, there is a little agent that you can use to capture the VGA frame and open a GUI to display the frame when you run the simulation. It's not great as an implementation. It was really, fast coding just to get something working. But basically, that's really the idea with SpinalSim, because you are in a software environment. You can open GUI, you can open TCP socket to branch, to connect yourself to the real world. So it can be test benches written in SpinalSim or in CocoaDB or in any software language, really provide you a lot of interaction with the real world.
I see. The next question is, would you comment on performance running Linux on SpinalHDL Scala simulation? Okay. Yeah, please go ahead.
Initially, I was doing the simulations using only Verilator. And when you do that using only Verilator, if you simulate the CPU running Linux with Verilator, I guess, I mean, I'm probably not very accurate, but you could get about 500 kilohertz, 500 clock cycles simulated per real-time second. And when you run a SoC, I'm seeing I'm about 200 kilohertz, so 200,000 cycles simulated per second when I'm running a SoC in SpinalSim, so with the Scala API. I mean, I'm not exactly sure of the number, but it's about those numbers, like 200,000.
Okay. Never mind. If it just was fine, and the performance, I guess, it won't be good because I'm running off very later after all. So yeah.
Yeah, the boot time. The boot time is it depends. Like, it's maybe 5 minutes if it uses the CPU simulated, and 30 minutes if it's the SoC. I'm really trying to avoid that, but sometimes I have to.
Yeah, I understand. I can fully understand. So, here's the one. Is it possible for you to implement RVP, the packaging the extension? I mean, I'm curious about it as well.
I guess it.
Yeah. Please go ahead.
I guess it would be feasible, but basically, for me personally, it's not really in my plan yet. But I guess it will be feasible. Basically, if you go in the VexRiscv README on the GitHub page, you can see there is an example of a little I am the instruction implemented in the plugin system. So for instance, even the FPU and all those things, they are implemented using plugins. So it could be not that hard to extend the core with, for instance, I mean, at least a subpart of RVP. Maybe we'll have issues if you have 3 operand instructions. We will need to extend the RISC-V to support 3 operand instructions. But I think somebody already did this kind of changes somewhere in one VexRiscv branch. So yeah, mostly it will require some work, but feasible.
Okay. Because this one's coming from me, I think that there's more important questions. So I'm jumping the ones I made. And how does Scala-based HDL to debug generated Verilog signal, NaN, renan, or Verilog when you use some common Verilog debug tool to verification your design? Okay, that was a good one. I'm curious about it as well.
Yeah, so it's a complicated question. So I'm trying not to avoid it. So tell me if it's kind of avoiding it. But basically, the thing when people ask me the question and when I think about it, the issue is that I'm not really hitting the issue. I think it's mostly related of your verification flow. Basically, I'm really not commonly looking at the Verilog generated. For me, the Verilog which is generated is just like assembly of C language. So,
yeah. Okay.
But I can understand that you need to look at it, especially when you start SpinalHDL, to understand how it translates into what you are used to see. And this I perfectly understand. So basically, the names that you use in the Scala will be preserved in the generated Verilog netlist as long as those names are linked by one way or another to the component you are in. That's the main. There is in the SpinalHDL documentation, there is a specific topic about how things are named. I recently added it, and it's not trivial, but it works great.
Okay, I believe that's very detailed. Yeah, I'm going to move forward.
Okay.
Someone's wondering, do you have benchmark data to compare with Shanghai? Oh, that is a RISC-V core being open source by recently, and it is stated that it is the most fastest softcore on the planet. I believe someone made that claim, and it's written in Chiso as well. But I don't think you have run it right.
I'm not aware of it, but that's interesting. I have to check that. So just one thing. I often say that the focus is about the clock per cycle, clock per instructions that the CPU does, and sometimes not really looking at how high the frequency goes. So, but I have to look at it. I really don't know.
Yeah, that's for sure. It is because there are so many RISC-V related news, so we're often missing out many things. So that's okay. And the last question on the Q&A will be, oh, okay. I will read out the comments on the YouTube later, but let's get the Slido down. Compared to object-oriented paradigm language like Scala, what will be the challenges to HDL-like functional language or even imperative paradigm language? I'm curious,
so first, Scala is not only object-oriented language, it's also functional programming language. So, I mean, if I understand well the question is about how hard it is to make internal domain specific languages in a functional language or imperative paradigm language. I think that's the question. Yeah. Like how to do an internal domain specific language. Right?
I guess the reason why is that for a functional language that everything is kind of parallelized. I'm not sure how to say, but immutable. Anyways, because the metrics of the imperative language like C or C++, there are many side effects of your what did you write, but for functional language, I believe that he's trying to say that the paradigm is preventing you to do dumb things, and so when you want to design a HDL, but it is hosted on another language like the Scala, or maybe someone wants to write a C, one want to write a kind of I don't know how to say it. That want to implement a new HDL, but is the host language is C. The barrier of this. Sorry, I don't know how to say it in English. Anyway, but yeah, I guess I can get the idea. Maybe we can continue this question on other platform. This is a good one, and I will check out. Is there any missing questions? Okay, then I will show up the language but I will show up the question that is on the YouTube.
Okay. So, will you suggest a newbie to skip Verilog, VXDL, and start learning SpinalHDL directly? So yeah, I guess yes. I mean, it really depends your approach. Like, I mean, it's a bit sad to say that, but if your objective is to get a work, I'm still sorry, but you have to learn VXDL and Verilog, because I guess for work, I mean, unless you know a company which is trying things and going on those new HDL, to get a work, you still have to do VXDL Verilog. This is for sure, and this is a bit sad. But if your objective is to learn things and have fun and avoid monkey coding, avoid copy pasting, and all those nasty things from VXDL and Verilog, yes, I would say yes, totally. A newbie can start directly with SpinalHDL, because one thing is SpinalHDL in some ways is much less abstract about what it infers in the hardware. You know, in VXDL and Verilog, it's a bit nasty. You have to infer things depending where they are written. They have different behavior. You have all the event-driven paradigm. This is not really hardware. This is another paradigm that we kind of translate into hardware. But SpinalHDL, you directly say, I want a register, I want a combinatorial signal. You say things much more explicitly than in VXDL and Verilog. So in some ways, it's much less confusing.
Okay, thanks. That is very, very clear. And we don't have further questions on either the YouTube or I guess we don't have any more questions. And well, maybe it's time to say thank you very much, and I wish you have. Oh, by the way, I heard that you were on the travel back then. Where did you go? I'm curious.
Holiday.
Okay, I see. Sorry, just sorry, dumb questions. Anyway, okay, maybe it's time to say goodbye and thank you so much. Ciao, Papom.
Thanks.
Yeah. Okay, bye.
Bye.